And so our next talk is going to be by Patrick Cousot, who's going to tell us how to obtain hyperlogics, of course, by abstract interpretation.
My co-author is somewhere. Where are you? Ah, he's there. So, interesting co-author. You should ask him questions. So let's go. We want to have a method to design hyperlogics. So you have to understand what is the semantics, what is the strongest property, what are the properties you are interested in, and then you derive the other one by consequence, and then you ask what are the proof rules, and I have the answer last year in the POPL paper. You start from a relational semantics, you identity to collecting, then you have some abstraction that go through the theory, and then Axel, Parks, and others goes to the rule. What is interesting, if you start by a structural fixed point definition, the calculus gives you all along the way structural definition, and so at the end, the logic will be by structural induction plus some argument for inductions. So the methodology is to calculate hyperlogic by structural abstraction of the program semantics. So I go to the conclusion, can we do it? Yes, but the problem is there is no abstraction in hyperlogic. So if you want to think something which is sound and complete, it's completely unmanageable. And the other way around is abstraction. And so I will follow this path plus at the end abstractions. So with semantics is interesting because when you have OR logic, you think it's for invariant, but assume you instead want history, that is, what are the paths that arrive at each point? Intuitively, the OR logic is the same. Unfortunately, you cannot apply OR logic. And this is because of the bad choice of the semantics, which was relational last year, and this year is better. It's an algebraic semantic. So what is an algebraic semantic? It's parameterized by a semantic domain, which is built out of two things. One is this set, which is description of executions. That is, semantics define properties of execution. So this is the finite one. Then you have implication and so on, union for handling if then else, and you have primitives. And another one is for infinite executions. And then your semantics will be three things. One is, for example, the assignment, how I go on after terminating, so this is a primitive. How I can escape using this assignment, it's impossible. How do I do not terminate with this assignment? It's impossible. It takes a break, you cannot go in sequence, you have to break, and you always terminate. So now what is interesting, and the only problem, is the iteration. So I define this operator. I want to know what is the semantics when I iterate in a loop and come back at the head. So there are finite execution. You say there is 0 iteration or 1 iteration followed by n-1 iteration. This is the backward one. There is also a forward which says it's either 0 or n-1 plus 1. So they are equivalent. Then I have another operator. So I will use this with induction, and this one with co-induction. You don't terminate if you make an iteration and then don't terminate. Then I can define the semantics of the while. How do I go terminate and go in sequence? I iterate and come back to the loop head, and then suddenly the test is false, or I start an execution of the body that does not terminate, that breaks, excuse me. I terminate by the test or by a break. So how can I use a while to break another external while? It's impossible. And here I consider how do I terminate when the body always yes, when I do a number of iterations and the body does not terminate, or the body always terminates, but I do it forever. So this is the semantic of non-termination, these two cases. Okay, we did. So it's algebraic because if I apply the paper of last year to these semantics, I get the classic paper on algebraic semantic, except that it is for an instantiation because they use states and so on. It's an instantiation of this. Okay, so now we have how to express properties. In logic, program logic, you have a language for program and a language for logic. And I've got a great idea that I took from Henner, which is we are only interested in program properties, so program properties can be encoded by a program. And this is the same idea as the two guys here who in their paper said program properties are recursively enumerable. So if they are recursively enumerable, there is a program that generates them. So we can define properties as program, and we have only one language. And then the others are abstraction. So now we need a property transformer, which is post. So post, you say, assume P, execute S, and then post will be true. What is it in terms of program? I execute P, so at the end I will have the properties of P. Then I go on in sequence, execute S, and then at the end I have the property of S when P. So we have the property transformer, and you can give a structural characterization. And this is the POPL paper of last year, except that now we have an algebraic semantic instead of a relational semantic. So you get the little q plus 2 points with the next talk. You get everything. Not interesting, so I go on. Now we move with hyper properties. And what is an hyper property? You have some semantic domain, in my case, termination, non-termination, and break. You put that in the triple. This gives you the semantic domain, and you take the power set, and you get hyper properties. The inclusion is implication, and you have a complete lattice structure, which is very nice. Okay. So we need to define an hyper property transformer. This is this one. You said you get an hyper property, you take any property inside, and you push with the property transformer, and you take the set of all these guys, and this is a Galois connection, so you think it will work. Then you try to have a structural definition of this operator, and you get a problem. And here the problem, I want to define the pose of the conditional, and I would like to say, like in all logic, I take the pose in the true case, I take the pose in the false case, and I make the join of the two. But it does not work. You see, you expand this definition, you expand this one, and you see here it's the same, it is the same P, whereas here it's different P's. So this lose the links between the property in the hyper properties. So many people say I take equal. This corresponds to an abstraction which is described in the paper. And so if you define the logic from there, it's always sound. But if your property is not closed under this abstraction, you are incomplete. Okay, so we have to find a workaround. It's very simple. If you take the pose of a singleton, it is a singleton of the property pose. So now I can rewrite this like this, and I take the singleton, and I get an equality. So we have a structural definition of pose, hyperpose. We apply paper of last year. We get a logic, and you over or under approximate, okay? And then this is the rule for the while. Don't read it, it's horrible. But what is interesting is if I have an hyper property, I execute, this one will be true. I want to prove that, and because it's sound and complete, it's only if I can prove that. And there you see I have to find a guy which is exactly describing how you come back at the end of the loop, at the head of the loop, and here you have to find a guy which exactly describe when I do not terminate. And if you make any approximation on one state, it doesn't work. So we have a logic which is not manageable, but sound and complete for any program property. So when you have a non-manageable computer science, you do abstraction. I'm lucky to have at least one that understands that. Huh? So remember, you went from algebraic semantic to program properties to hyper properties to logic. So we can do an abstraction at this level. For example, I had the semantic with traces. I go to relational semantics, and I get an abstraction. Or here, for example, I had hyper properties here, and I do the union of the hyper properties inside, and I get the classic properties in OR logic. Or you can do an abstraction here. And so this is the main contribution. So yes, the first one is if you do, excuse me, I forgot something. If you do an abstraction here, it propagates here. If you do one here, it propagates here. And so at each level, there is possibilities. And the interesting thing is if you do an abstraction of the semantics, it is still another instance of the algebraic semantics. So that's why it's true. Okay, so let's go to hyper properties. There are a dozen in the paper, many done by Jeffery. And we have a lattice of all properties, which someday will be a cube, I'm sure. And if it's a cube and you are popular, if not a cube, no one remember. So, so I will describe this point here. So it's a chain limit order ideal abstraction. Very nice. What is it? In fact, it's a generalization of forall-exists abstraction. So the forall-exists hyperproperty. It is for traces. So you instantiate my complete lattice that I have at the beginning to set of traces. And then the forall-exists are hyperproperties, as a set of state that are, so that if you have any trace, there exists another one which is related according to some relation. So that's the general definition. Okay, forget about this and consider the abstraction. The only problem is loops. So if you have an hyperproperty P, and you imagine I have some property for the first iteration, another one for the second, for the third, and so on, and you have no way to say, to pass to the limit, then you are in trouble. So we say, okay, we consider the cases where you can pass to the limit. And then you have so this is a closure operator. And we take this one, which says, when you have a property, we consider all the one below. Why? It's because when you iterate to this fixed point, you start anywhere from below, you will reach this fixed point. And so now you have solved the problem if the function is continuous. Because infinitely many iterate, you have finite. But if it's not continuous, and this is the case here, when you compose these two guys, then the operator, they are just extensive and increasing, and so not idempotent. And so you have a problem because if it's going higher order in the iteration, you will not make it. So the solution is very simple. It's a theorem I had in the I don't remember. It's a Portugalia Mathematica. And so you take the fixed point of this. So essentially, it means iterate infinitely many often, take the lub, reiterate infinitely many often, take the lub, reiterate, and so go in the hierarchy of ordinals, and at the end you will converge, and this will be the operator you want. So this is a Galois connection. So you apply a POPL of last year, and you get the logic. And what is interesting is that if you instantiate for traces, then you get the always exist hyperproperties. And so because we have a logic for reasoning on that, we also have a logic for reasoning on that for the specific case where the semantic is set of traces. Okay? Conclusion. So my standard conclusion is we are the best. So, so I have to prove it. So, so we have introduced a new algebraic semantics. We have that. We have considered the program as properties. Okay. We have designed by everything by the method of last year. Okay. And we have a general algebraic hyperlogic sound and complete, but no one will ever use it. And we have this includes terminating, non-terminating things. And so at this point, we did some abstractions. And if you consider an abstraction of the algebraic properties, they are less expressive. You limit what you can say, but you can get a sound and complete logic to handle this class of hyperproperties. And we illustrated that by forall-exists. And then my co-author said, yeah, but you have forgotten 3/3 of the paper. Okay, so yeah, in the paper, many other things, various instantiations of the logic, many abstractions of the hyperproperty I have shown, including exists-forall and forall-exists, which my co-author is very proud of. Okay, so also he corrected a few errors that he found in the literature, and he was happy. So now I have a conclusion of the conclusion. If you do not read the paper and understand nothing in the talk, you can always remember that a transformational OR logic is an abstract interpretation of an hyper-transformer of an instantiation of an algebraic semantics. It's already hard to remember that, huh? But, but you can also have the inverse, which applies to the previous talk. You see, it says, people that say, oh, I can do nothing, I will define a logic. So they start from saying, I have this rule, this is a logic language. And so what are they doing? They define an hyperlogic or logic, which is a complicated way of defining an abstract interpretation of an instantiation of an algebraic semantics. And why is it complicated? Because the rules don't tell you the whole truth. For example, you have made an abstraction, it doesn't tell you what it was. You have used an induction principle, it's hidden in the rules. You want to prove that two proof methods are the same, what do? We say, oh, they do the same abstraction, so they are the same. Whereas they have to prove any proof in the one, I can do the other, and the proof of the other, I can do the first. And so reasoning on proof system is not good for me, maybe for you also. So here I'm done. You see, I made it in time.
You were even 30 seconds early, so we have time for several questions.
Peter.
Yeah, thank you. So one could argue that besides soundness and completeness, another important property of a logic is how natural it is to apply it, right? How naturally it captures the reasoning principles. So how applicable is a logic that you construct this way?
Yes, so this is essentially the question, why completeness? And completeness is very important because it's not understood. I don't know why. That it takes the system, you are odd if you are 0, or some even if you are 0, or even plus 2. Now, I can prove 6 is even. But I can also prove 5 is not even. I say, to prove 5, you have to prove 3. To prove 3, you have to prove 1. And 1 you cannot because there is no axiom. And so if you have OR logic, you can do the same. This is not false because I cannot do the proof. And this is not true. But if it's incomplete, you cannot do that. So you lose some power when you have an incomplete logic.
Do we have any other questions?
Yeah, the way I see it, the problem with completeness is that when you're trying to do relational proofs, it's actually not too hard to get completeness if you can be relatively complete by reducing your relational reasoning to unary reasoning. But that's not the proof you want to write. There are other proofs that are possible if you have other reasoning principles that are inherently relational that are not captured by being complete or not, because they're just additional rules that you can add that unlock different proofs that you cannot do with a complete logic that only has a reduction to unary reasoning.
If you are incomplete, additional rule may not be enough to get completeness.
Yeah, but you have more proofs, and maybe some of these proofs are easier to do than one.
Yes, so, but I have abstraction to do easier.
Right.
You see, my answer to easier is do some abstraction. It will be easier.
So we have time for one last question while the next speaker sets up. Is there any?
Can I see the last slide before the conclusion?
The last slide before the conclusion was, I don't know, remember what. And anyway, you cannot because she has to.
Okay.
So
there was an inclusion rather than an equality, and so what I want to ask if this affects the completeness of the corresponding hyperlogic or not. There was an inclusion, not an equality.
Yes. So this, you get an equality if you consider an abstraction of the hyper properties, so that this abstraction will give you the equality. So you really complete in sense that the proof method of Dardinier and Müller will always be sound. And if your property is in this class that is closed by the abstraction, it will be complete, which is a nice result and easier.
So on those words, let's thank the speaker again.
Yeah.